picture. Right, so co-multiplication takes this picture to that picture. So this is kind of two copies of the picture on the left. And the monodrome is L plus and L minus. Go to monodrome is delta of L plus and delta of L minus. All right, and finally, we've seen what R matrix does. So conjugation by the R matrix, by the universal R matrix, corresponds to taking this picture, which can represent standard square of the quantum group, and just swapping two punctures. Oops, sorry. All right, so that's what we've seen last time, and let me also just remind an example how it worked in case SL3. So this was the quiver. So I'm now drawing a quiver representing the a quiver which gives one cluster chart of this quantum cluster variety. Sorry, these are frozen. Then we've seen the kind of SL2 triples. So the generators E1, F1, and so on, they just depend on these variables here. The generators E2, F2, and so on depend on these cluster variables here. And the Casimir's can be expressed via these two cycles. Okay, so yeah, mark it. So this is root alpha 2. This is root alpha 1. And these here are Casimir's. Or rather, Casimir's are elementary symmetric functions of those. Okay, good. So that is a reminder. Now, what I want to start today, I wanted to start by discussing so-called positive representations. And these are representations of quantum cluster varieties. So let me start. I won't give a precise definition, but it'll just start by an example. So if we take a quiver Q, and let's say this quiver is it just consists of 3 nodes. Let's call them, node 1, 2, and 3. Then, well, what's the corresponding quantum torus? It's TQ. This is just an algebra, again, of rational functions of parameter Q, generators Y1, Y2, Y3, and their inverses. And relations, well, Y2, Y1, Q square commute, Y3, Y2, Q square commute, and Y1, Y3 just commute. And moreover, we can see that the product Y1, Y3, this is actually an element of the center of our quantum torus TQ, right? So that's that thing over here is a Casimir. All right, then how we construct a positive representation of the thing? We choose, well, effectively, we will be just mapping it to a Heisenberg algebra and writing the most naive representation of the Heisenberg algebra. But more precisely, we take P to be some normalization of d over dx, its operator in X. We then we choose a real number B, and we set Q to be e to the pi I B square. So in other words, we see that Q is on the unit circle, and then we choose two more operator P uppercase, which is just by definition e to the 2 pi B P. So this is an operating acting on functions of x by shift, right? It shifts by 2 pi b over 2 pi I. And we have another operator x, uppercase x, with just x by multiplication by e to the 2 pi bx, right? So then what we see is that if you try to commute one operator through the other, you get e to the, well, just by Baker-Campbell-Hauser formula, you should take a commutator of these parts. So this becomes 4 pi square b square commutator of p and x, uppercase x, uppercase p. And this becomes, you calculated q to the minus 2. Well, let me actually write it out. It's 4 pi square b square over 2 pi I xp. Sorry, e to the power. And this is just q to the minus 2 xp. All right. And then the representation that I would, yeah, actually, before I do that, let me just make a remark. So how these operators x and p act. So x, once again, just, oops, sorry, acting on the function f of lowercase x. This is just e to the 2 pi bx f of x. And p acting on f of x. This is f of x plus the commutator, 2 pi bp commuting with x. And this is just f, if we remember what p is, f of x plus 2 pi b over 2 pi I d over dx commuting with x. So this is just f of x minus ib. So this is shift by ib, right? Once again, this is multiplication. This is shift by minus ib. And then to write, so at the end of the day, we still want to write representation of this algebra. And the way we would do that is as follows. We just take the same quiver. And I'll call these nodes now y1, y2, and y3. And I want to make an assignment. So I'll just, again, just in this example, I'll choose one. So what happens now is indeed a choice. I'll just set, for example, y1 to p and y2 to x and y3 to, say, lambda minus p. And the only thing I require is that if I take the commutator of yj and yk, this is 1 over 2 pi I epsilon jk, where I remind that epsilon jk, this is just adjacency matrix of this quiver. So for example, indeed, if I take a commutator of y1, which is p, and y2, which is x, the commutator of y1 and y2, which is commutator of p and x, is 1 over 2 pi I times 1, and this is exactly 1 from having this one arrow here, right? And these two commute, right? And then when I write a representation, I just set yj to be e to the 2 pi b yj. So for example, y1 is e to the 2 pi b p. So this is our operator p uppercase. Right? And in general, all of those cluster variables will just act by some monomials of operators p, x, and some elements lambda. So element lambda just commutes with everything. And so for each Casimir of for each generator of the center, there will be some variable lambda that just commutes with everything, right? And if we do this assignment, if we do this assignment over here, then we can see that the relations which need to hold, they hold. So yj, yk would just commute by q to the 2 epsilon kj, yk, yj as promised. All right, now I've just written some operators. I didn't explain which functions they act on, and I won't. But let me just say a few words about the space of functions. So this algebra generated by, actually algebra over rational functions of q generated by p and x. This algebra acts on rapidly decaying functions it's rapidly decaying functions. Well, let me be precise. So they're functions from a line. They're rapidly decaying functions from complex line to complex line, but they're rapidly decaying functions along each line of the form R plus IS for any real number, for any real number S, right? So they're just so if you wish, you can think of functions, complex valued functions on the line that are rapidly decaying. They also have analytic continuation, and this analytic continuation rapidly decays along each of these horizontal lines. Now, I don't want to specify what means rapidly decaying, but you can probably guess what it means just by knowing that multiplication by e to the x should act, multiplication by e to the x should act on these lines, and shift in the complex in the vertical direction should also act, right? Right. So, in fact, to be more precise, the following. No, sorry. In fact, this family of functions of the form e to the minus alpha x squared plus beta x times p of x is what is called? Sorry, I'm blanking on the word. Sorry, is dense. Here I go. Yeah, sorry about that. Is dense in our representation in our space of functions. And here alpha is greater than 0, and beta is a complex number, and p of x is a polynomial, polynomial with complex coefficients, right? So clearly on these functions, you can act by multiplication by e to the x, or e to the constant times x, and you can shift in imaginary direction, and that's still defined. All right, now I just would like to warn that both p and x they're kind of at the same time nice and not so nice operators, because they act by unbounded, and that's rather important. Unbounded essential self-adjoint self-adjoint operators with a positive spectrum. Actually, continuous and positive spectrum. Right. So sorry about that. Right. So unbounded just means that if we want an honest representation, we would need to choose the maximal domain in which they act, so that we have different analytic difficulties there, but everything ends up working nicely. Now, and still, what we just discussed, this is just so we just constructed a representation of a single quantum torus, but we would like to construct a representation of the whole global algebra functions. So how does this work? So idea behind representation of the whole algebra, of the whole algebra, this LQQ, where Q is our quiver, is as follows. So you take this algebra, you embed it into a single chart. So I'd like to remind that this algebra, so although I write quiver Q, right, this algebra doesn't really depend on a single quiver, it rather depends on all quivers in this mutation class, right? So we start from one quiver, we start to mutate it, and then this algebra depends kind of simultaneously on all, well, doesn't depend on each single quiver, but depends on all possible ways to to mutate this quiver, so no possible chart. And this is a single chart, right? So this is like you have a variety, you have a chart on this variety. So this is an algebra, and this is a localization of this algebra at some divisor. And then we've seen that we can act by this one chart on a representation VQ, and let me start labeling things here. So this thing here is a quantum torus, or a single quantum chart. This thing here is this positive representation of a single chart. So this Heisenberg algebra representation, more or less. But then what can happen, obviously, is we can, maybe even before I do that, we can, so here when I construct representation, I just made it an arbitrary choice. So for example, I call this P and I call this X, and I could have as well make this minus X and make this P, but by Stone-von Neumann theorem, all those things are unitary equivalent. So at the end of the day, this representation doesn't depend on a particular, well, up to unitary equivalence, doesn't depend on a particular assignment of what is P and what is X. As long as these commutation relations are satisfied, we're fine. It's the same representation. But what can happen is that we embed into a different chart and do a different representation. And then when we pull back both of these representations to this algebra, it might as well happen that these representations are different. And in fact, it doesn't happen. So they are the same and they're related by the following transformation. So we know that from chart to chart, we can go by just by a cluster mutation. So by conjugating by quantum dilogarithm of some variable, let's call it yk. And therefore, so what happens really here? We have an algebra of operators, and the conjugating operator by some other operator, this psi q of y. And this means that on a representation, so when we conjugate a matrix, say we have a matrix A, and then we conjugate matrix A by CAC inverse. And if we were acting on the vector V, if we want still to act in the same way, so it's just a change of coordinates, we have to act on C by matrix, on V by matrix C, right? So what we really want to do here, we just want to act, by this function, just act on representation. But that's a problem really, because because when we're constructing these representations, we set Q to be on the unit circle. And if Q is on the unit circle and we honestly write series for this function, we will see that this thing actually diverges when Q is on the unit circle. But luckily, there's a way out. So this thing is replaced by so-called Faddeev's non-compact quantum dilogarithm. So this is Faddeev's non-compact. So again, this is just a name. Quantum dilogarithm. And then when it's replaced, this action by this function becomes unitary equivalence. So what happens is that somehow instead of just, so when you take a representation described above of one quantum chart and of the other quantum chart, and you pull them back to the same algebra, to our quantum cluster variety, you get two unitary equivalent representations. Or equivalently, you can think of this as you have a single representation and this infinite pool of unitary equivalences that are controlled by the combinatorics of the quivers, by quiver mutations, right? Right, so maybe I should just comment that when I write this kind of lowercase yk over here, it's just a matter of it's a matter of notation, indeed. So when people speak about this non-compact quantum dialog, they don't talk about this uppercase y, but rather of their logarithms. So this lowercase y, and maybe just again a remark that. We've seen last time that this uppercase, so this usual quantum dialog satisfies this condition. And this is really a kind of condition for the, it's an analog of a gamma function. That's what people call Q gamma function. Q gamma function condition. And this is, so on the level of this non-compact quantum dialogues, you can write the same thing. So the same thing will be phi of y minus IB over 2 is 1 plus e to the 2 pi b y phi of y plus IB over 2. Or same as 1 plus y uppercase phi of y plus IB over 2. So we see we see that and it's the same. It's really just the same equation written here, maybe with a shift by q, right? So we just replaced here y by q inverse y. All right, now let's see an example of how this works. Example. Let's take our favorite quiver for UQSL2. And choose a single, choose some way to write its kind of logs of its variables in terms of p and x. So we can choose here p plus lambda over 2. We can choose here x minus lambda. We can choose here minus p plus lambda over 2, and we can choose here minus x minus lambda. And you probably remember from last time that we actually have, so the kernel of the adjacency matrix is two-dimensional. So we have two Casimirs. So the center is generated by two elements rather than one. And I only specified kind of one free parameter here, lambda, and we'll see why that happens in a second. Let me just write what generators of the quantum group go to, right? So E goes to this guy plus the product of those, right? So E is e to the 2 pi b p plus lambda over 2 plus e to the 2 pi b, and then sum of these things. So it's p plus x minus lambda over 2. Right? F goes to, well, similar thing, e to the 2 pi b minus p plus lambda over 2 plus e to the 2 pi b, and then sum of, sum of these things. So it's minus p minus x minus lambda over 2. K goes to product of all these three. And here everything cancels out except for x. So it's e to the 2 pi bx. And similarly, k prime goes to e to the minus 2 pi bx. And we see that the Casimir kk prime is equal to 1. And therefore, if we indeed set this Casimir to 1, we indeed get a representation of UQSL2 rather than its Drinfeld double of its Borel. So this is just a condition that we talk about the quantum group, representations of the quantum group. And finally, the Casimir C, which we've discussed last time, and remind this time, goes to e to the 2 pi b lambda plus e to the minus 2 pi b lambda. In other words, and as soon as we picked the central K, as soon as we picked this lambda, we completely defined the representation up to unitary equivalence. And this is what people call positive representation of the quantum group. So P lambda defined this way is a positive representation of UQSL2. And as far as I understand, the word positive here comes from the fact that the spectrum of all the Chevalier generators in the center, it's positive. And pictorially, I'll just denote this representation so pictorially, well, somehow this representation is completely defined by just this surface specifying the group of like when we talk about the surface, we think of surface and G local system on the surface, right? So in this case, G is equal to SL2. So as soon as we specify the group and the surface and specify the central character lambda, we specify the representation, right? So that would be my kind of drawing for this representation. And now I said that kind of having all these cluster mutations is beneficial. And indeed, if you just mutate at node 2, what will happen, operator E will just become this single variable. So it will become just e to the 2 pi b p plus lambda over 2. So it becomes easier indeed. And so again, now up to kind of unitary equivalence, it's just a multiplication operator really. Well, right now it's a shift operator, but you can always do a Fourier transform. But operator F becomes more complicated. It has 4 summons. All right. Now, let me just to advertise these representations more, let me say a few more facts about those. So I'll explain why they're interesting, and then try to explain some facts about them. Right, so why they're interesting.
Is there a educaционный комитет, который...
Ой, Андрей, у вас включен звук. Sorry. Oh, he disappeared. Right. Right, sorry. Right, so yeah, why they're interesting. So one more cool fact about them is, let me again just try this operators, the shift operator and the multiplication operator. And let's remind that q is e to the pi I b square. But remember, b was just a real number here. And what we can do, we can say, okay, fine, let's see what happens if we replace b by b inverse. So let's set p check to be e to the 2 pi b inverse p, x check to be e to the 2 pi b inverse x, and q check to be e to the pi I b to the minus 2, right? So b inverse square. And then we can see that, well, first of all, just the same calculation as we've done 5 minutes ago, or 10 minutes ago. P check Q check is Q check to the, sorry, P check X check is Q check to the minus 2 X check P check. So just another copy of, so this is just another copy of this algebra, really, when you replace Q by Q check. But then what's more important is that, well, obviously when you commute P and P check, they just commute, right? And when you commute X and X check, they just commute. What's more important is that when you commute P and X check and the P check and X, sorry, X and P check, all of those commute. So you have really 2 copies of the same algebra commuting. And indeed, let's just check that it works as promised. So if you do e to the 2 pi b, sorry, 2 pi b p times e to the 2 pi b inverse x. So what happens? It's sorry, and this is, of course, I'm just writing p x check. So this is e to the, well, their commutator, and their commutator is 4 pi squared, because b and b inverse well, cancel out. So it's 4 pi squared over 1 over 2 pi I x check p, and well, this is what minus 2 pi I, right? So this is e to the minus 2 pi I x check p. So this is just x check p. So you have 2 commuting copies of the algebra, and moreover, well, it's a corollary of what we just seen, that this p lambda is a uq SL2 uq check SL2 bimodule. And that thing here is what people call modular double. Modular double of UQSL2. And indeed, when we, so before mutations were implemented by conjugating by this quantum dialog over here, and this thing just depended on Q, but phi actually depends on B and B inverse in a symmetric way. So maybe I should write it here. Note phi B of y is the same as phi B inverse of y. So when you can do this mutation, you simultaneously do a mutation of the whole modular double, not of just one quantum group. All right, now what is known about positive representations? So first, I guess, goes back to Poisson and Teschner. It's around 2000. So they showed that these positive representations are actually closed under taking tensor products. And what it means really is if you take two positive representations, P lambda and P mu, you get a direct sum, but since we work with infinite dimensional spaces, you actually need to take a direct integral. So this is just a replacement for a direct sum over R plus of this representations P nu, and then we sort of replace a sum by an integral, and then you have to put some measure. So this is just usually a Lebesgue measure. Now you can see this funny effect that the right-hand side does not depend on lambda and mu. And this is of course surprising, but on the other hand, not so surprising, right? Because it just says that if you take two representations of SL2 and you tensor them up and decompose them to reducibles, you just see that all representations appear with multiplicity 1. And this is precisely this effect that you just see that all representations appear with multiplicity 1. But now in the finite dimensional case, the range of those representations, it depends on lambda and mu. And in the infinite dimensional case, you kind of get the whole line, so the whole range of these representations. And this is actually similar effect holds for the usual principal series representations for just the universal enveloping algebra. Although for the principal series, they're not closed under tensor products. They are you have kind of this infinite part plus also some discrete series. And here it's nice. You only, when you decompose, you only see principal representations. You only see positive representations. Then second thing that was done really is it goes back to work of Frankel and Ip, and then just Ivan Ip on his own. So it's a range of papers. It started in 2013 and on. And what they did, they defined these positive representations for UQG, and here G is just any simple Lie algebra, Lie algebra. They showed that this P lambda is actually again a bimodule for UQG, and you check G check, where this G check is Langland's dual to G. So this is Langland's dual to G. So this is just another super interesting property of these representations. Now, unfortunately, well, just this statement is a slight lie, just the way I formulated it, because some generators of UQG, instead of commuting with those, they commute by a factor of -1. But if instead of that you take what people call locally finite part of the quantum group, and this is a finite index subalgebra, then this is not a statement, right? So this is kind of morally, this is just a tensor product of UQG and UQ G check, but you have to be slightly more precise to make it correct. And finally, then Gus, Schrader, and myself, we proved, so 2017 or so, we proved that for SLN, here that happened for UQSL2. And we proved the same statement for UQSLN, so almost the same statement. So if you tensor multiply P lambda and P mu, you get again direct integral over a positive Weil chamber of P nu tensor. Sorry, this is nu M lambda mu nu. Sorry, and you need some measure over here. So for G being SLN. Now, what's what here? The C plus is the positive Weil chamber inside Rn. This is multiplicity space. which we haven't seen in SL2 case, as we shouldn't have. Multiplicity space. Now, all representations here are infinite dimensional, and multiplicity space is infinite dimensional as well. But we'll see what it is more precisely in a second. And this thing here, it's some known gadget. So for experts, this is Kleinian measure, but again, it's not actually that important. Right. All right. So in other words, I just wanted to say that these representations are interesting. They form at least so far, they kind of tend to form a monoidal category, which is just a fancy way to say they're closed under tensor products. And they have to do something with they give you bimodules for kind of quantum group and kind of quantum version of what Langlands do. All right, now I'd like to show idea of proof of this statement for SLN, but I'll just actually show the idea for SL2. All right, so let me try to do that. Maybe I should stop for a second and ask if there are any questions or comments. Well, okay, if there are no questions and comments, I'll just continue then. Right, so idea of proof. Idea of proof is as follows, right? So, all right, I'll just start a new page. So so how do you really decompose tensor product of two representations? Well, let's see. So first of all, how do you act on the tensor product? You take quantum group, you take the coproduct to embed it into two copies of the quantum group. And then you act on this tensor product P lambda tensor P mu. Or inside here you had a Casimir Ci, so it was a central element. Inside here you have a delta of the Casimir, right? But the trouble is that, well, the Casimir was inside, it was sitting inside the center of the quantum group, right? But delta of Ci is not in the center of the tensor square of the quantum group. And if you want to see kind of how this product decomposes with respect to embedding of UQG inside here, then what you need to do first, you need to diagonalize these operators, right? So that the center of the quantum group acts just by multiplication, right? Sorry, and here, of course, I want to say that it doesn't belong to the center.
I get embedded diagonally, right?
Sorry?
Delta means diagonal embedding. But does it
mean?
This
is just diagonal embedding, just multiplicate, just with co-multiplication.
Does it mean x1 plus x2, or does it mean x1 times x2?
No, it means so it means if we're talking about universal enveloping algebra where the co-multiplication is commutative, so for U of G, would have delta of x would just go to x tensor 1 plus 1 tensor x.
That was my question.
Right, but for a quantum group, the co-multiplication is not commutative. So rather, for example, delta of E goes to E tensor 1 plus K tensor E. So it's this type of action, but it's not commutative. Right, yeah, thank you for the question. All right. Great, and right, let me just put it down. So to diagonalize or sorry, to decompose this tensor product P lambda tensor P mu, we just need to diagonalize the Casimir's Ci, right? And indeed, let's see on an example how this works. So let's say G is equal to SL2, and what's our surface that corresponds to the two copies to the tensor square of the quantum group, right? It's that thing over here. So we have two marked points, two punctures, and so if I want to talk about clusters, I really need to choose triangulation to figure out kind of which coordinate chart I'm using. Let me remind what the quiver is here. So again, quiver coming from, in SL2 case, it's just coming from, standard quiver for triangulation, and the standard quiver in SL2 is you just put variables on the cluster variables on the edges of triangulation, and the quiver becomes like that. So let me redraw that because it's impossible to see. Let me label the variables. So it's 1, 2, 3, 4, 5, 6, and 7. So this is 3. All right. Now, what happens with the generators of the quantum group? Well, let's just try them out. So delta of E goes to, I guess I'll probably bore you with that, but let me still I just want to make one point. So delta of E, so before that, it was kind of the monodromy just across this part, but now it's monodromy across this whole thing. So if you spell it out, it becomes Y1, so YE1 plus YE1 plus E2 plus YE1 plus E2 plus E3 plus YE1 plus dot 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 plus E4. And once again, when I read this subscript, E1 plus E2 plus E3, that just means that I multiplied Y1, Y2, and Y3 and put some appropriate power of Q in front, right? So delta of K similarly will be just the product YE1 plus dot 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 plus E5. And as before, delta of F is just theta of delta of E, meaning that I just need to rotate this picture 180 degrees. And so delta of F will be this times product of these two times, plus product of these two, plus product of these three, plus product of these four. And similarly, K prime, delta of K prime is theta of delta of K. So theta here is 180 degrees rotation. In particular, that thing here is YE5 plus E6 plus E3 plus E7 plus E1. But then now if we think of what is delta of the Casimir, right? Remember, it should be a product of E and F minus K prime. And this thing becomes, it's some Q difference operator with 14 terms. It's a bit tough to diagonalize any such thing. And why is it so kind of, how do we see that this thing is so nasty? Well, because really some of the complexity of this expression for the Casimir, this really depends on how many triangles the monodromy that it's a trace of crosses. And here the monodromy crosses these 4 triangles, but also some of them crosses twice. So that's a rather nasty expression indeed. But since we have this tool of cluster mutations, we can just choose a different cluster, so different presentation in which this Casimir becomes nicer and simpler. And so let me show how it works. So different cluster. And again, I'll choose the same surface. But I'll just draw it slightly differently. So it will be, again, two marked points as before and 2 punctures. Let me just put them vertically. It doesn't really matter. Everything is topological. And I'll choose a triangulation like that. And then the monodromy that tells us what happens with the Casimirs, it sits over here and it crosses just 2 triangles. And let me just shade them. So it's those 2 guys. Right, so we don't see the outer triangle and we don't see this inner self-folded triangle. And if we can zoom in, well, sorry, pun is not really intended, into this cylinder in which the monodromy sits. let me again just draw all the variables. Oh, sorry, all the variables that are here. So these are these three and these three, and if we draw what happens with them, so have these kind of sorry. Yeah, so we have these arrows, and then, well, I guess these arrows. Okay, sorry, it's a terrible picture, but let me redraw the quiver. And variables 1, 2, 3, 4. And if you honestly write what the monodromy is, you actually see that. Well, maybe let us just do that. So first of all, what's this cylinder over here? We can think of the cylinder as just a square. We choose one diagonal, right? And then we identified the sides, two sides of the square. And what are all these variables? So these variables sitting at the edges of our square. Here's our arrows. So we have vertex 2 on the bottom, vertex 4 on the top, vertex 1 in the middle, and this is what vertex 3 is. These sides just get glued together. And if we then recall these pictures that this black-white networks that Sasha was drawing, so let me recover them. It's a dual graph to our quiver. And write a monodromy that goes from the left to right. We'll see that. Oops, sorry, once again. So let's see what the monodroming matrix is. We have variables y3 sitting over here and variable y1 sitting over here, and I'm not writing anything here just because in reality, so this is the same face, and we have a product of this variable and this variable sitting in this face when the face is identified, when we glue, right? So what's our matrix, right? And let's remember that well, our delta of the Casimir in this cluster just becomes trace of the monodrome M. And how to write monodrome M? Well, first we write M tilde, which is just honestly path counting along this graph. So this is let's do that once again. So when we go from 2 to 2, there's just one way to go, and therefore there's no y's lying below this path, so we'll put 1. From 2 to 1, there's one way to go, and only y3 lies below that. From 1 to 2, again, it's just 1. And from 1 to 1, there's this path, and which gives us y1, y3, and there's this path, which gives us y3. So this is, this is y e3 plus ye1 plus e3. Right, but unfortunately, this matrix, we need to normalize it still. So determinant of this M tilde is y e1 plus e3, and so we need to divide by the square root of determinant. So M, the real monodromy, is M tilde divided by square root of determinant, and therefore this trace becomes when we divide by so we have to subtract for all these indices. We have to subtract 1/2 of e1 plus e3. And what we get is y 1/2 e3 minus e1 plus, let me write it here, plus y 1/2 e3 plus e1 plus y minus 1/2, or maybe 1/2 minus e3 minus e1, right? And now, as before, we can choose any, we can make this y3 and y1 to act in any way we want, as long as the commutation relations are as we need. So for example, we can set this y1 to act by p minus x and y3 to act by p plus x, and indeed the commutation relations will be as needed. So except for maybe I should have changed the signs. Maybe this should be, sorry, P. I guess this should be P plus X and this should be P minus X. Right, then P with X give us one arrow and minus X with P gives us another arrow. And then when we calculate what operator this becomes, so E3 minus, so yeah, the first summand becomes e to the minus 2 pi bx, and then other two e to the 2 pi bp and e to the minus 2 pi bp. And we can recognize, okay, first of all, it's much simpler Q-difference operator, you just have 3 terms rather than 14. But what's better, it's a well-known operator. This is what people call Hamiltonian of, so this is Hamiltonian of open quantum SL2 Toda chain or Toda system. Right. So at the end of the day, we just need to diagonalize this one Hamiltonian to decompose, to solve this problem of decomposing tensor product of two positive representation. And let me just finish this SL2 story, and then I'll go to SLN, and finally we'll be able to get to this Gelfand-Zeitlin representation. So there's a theorem. As far as I understand, this is resolved by Kashayev. So that, well, definitely I've learned it from his papers. So there exists a family of functions psi lambda x. So they depend on two variables, lambda and x, such that when you act by h on the psi lambda x, you get e to the 2 pi b lambda plus e to the minus 2 pi b lambda eigenvalue. And well, clearly, yeah, I'm going to write psi lambda x. So psi lambda x is an eigenfunction for the operator h with this eigenvalue. So exactly the central character of positive representation. And second statement, which you always have to worry about when you talk about infinite dimensional spaces, is that you have to actually say that these functions they actually form an orthogonal and complete family of eigenfunctions, right? Because you can't just count them, right, as in finite dimensional case. So as you let lambda run over positive part of R, and the positive part just comes from the fact that you see this is kind of symmetric when you change lambda to minus lambda. So this family these functions form a complete and orthogonal system of eigenfunctions for the operator H. And kind of simple corollary from there, and it's the kind of the end of SL2 story, is that if you take P lambda tensor P mu, then you actually have an isomorphism with this direct integral over R plus of P nu d nu, and this isomorphism goes as follows. So if you take some function f of x, then this function is sent to integral of integral of f hat of nu psi nu x d nu, where phi hat nu is once again is just an integral of f of x psi nu x bar dx, right? And this is unit equivalence. So in other words, what happens is we kind of we take a Fourier transform of f of x. So this transform, almost a Fourier transform, just our kernel is different than usual in the Fourier transform. but we take a Fourier transform and then decompose f of x into these Fourier modes, right? So this is really called Whittaker transform. Right, and the fact that these functions are complete orthogonal complete really tells you that, okay, well, you can do this transform, but then you can also do the inverse of the transform, and well, this transform has an inverse. All right, so this is the SL2 story, and yeah, maybe once again, are there any questions? I'll be happy to pause and maybe explain if. All right, so then I'll just go to high rank case. Right, so what happens in high rank? Oh, sorry. So in high rank, well, let me again do just example of G being SL4. So you see how in this whole process, we kind of ended up zooming into this quiver if we choose a nice chart. So what will happen in SL4 example, the quiver that we'll be zooming in will be as follows. So it's kind of, we see the same double arrows, but just more of those. And as before, we kind of, so this is just part of the quiver that we're interested in, but then there are some quivers that attached to it from the top and from the bottom, just as in SL2 case, we had these triangles that we didn't take into consideration. So same happens in high rank. Well, still this delta of the Casimers are they go to these traces in fundamental representation of the monodromy, and now it's a more, if we do the same trick as before and think of this quiver as a quiver lying on the cylinder, the dual black-white graph will give us the following network. So when we direct it, it will look like this. Yeah, like that. And so we can calculate traces of the monodromy, and we can write out explicitly in terms of just these 6 variables over here. We can write the Casimers, and what will happen is that when you write them out in this representation, they will actually just become the ith. So the Ci, well, delta of Ci will just become the ith Hamiltonian of the quantum open SL4 total. All right, now if we want to now diagonalize this product, P lambda tensor P mu, so what you want to do, you want to diagonalize all of this delta of C1 dot delta of Cn. And what will be happening, you'll be getting this direct integral over, well, now positive chamber of this, as I've written, P nu tensor M lambda mu D some measure of nu. Now, what's what over here? So this thing is just the kind of nu1 dot nu n eigenspace. This is the multiplicity space. Sorry. All right. Now, how does the diagonalization process go? Well, so diagonalization. Well, it's again for SLN. It's in my paper with Gus that there exists orthogonal and complete family of eigenfunctions, functions psi lambda of x, and now they depend on vector lambda, vector x, right? Such that when you apply hi to this psi lambda of x, so remember hi is an operator, is a q-difference operator in x, in e to the x and e to the d over dx, right? So we act on this x variables, and the eigenvalue is just the ith elementary symmetric function of expressions e to the 2 pi b lambda 1 dot 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 e to the 2 pi b lambda n, oops, sorry, psi lambda of x, where we impose condition that lambda 1 plus lambda n is equal to 0. So in SL2 case, this will be just e to the 2 pi b lambda plus e to the minus 2 pi b lambda, right? Right, so this thing here is ith elementary symmetric function. And this thing is what people call a B Whittaker function, kind of quantum analog of the Whittaker function for for universal development algebra. All right, and then as soon as we've seen that, we can ask, okay, right. So we started from some representations that came from some cluster story, and we did this diagonalization process. And do these things have any cluster interpretation? And the answer is actually yes, they do, and it's quite interesting. So, well, let me write a question. So, do this P nu and the multiplicity space have cluster interpretation? And the answer is yes. And the interpretation is as follows. So if you look at this, what we've been doing, so our original surface, right? It was just we would take this disk with 2 marked points to punctures. We specify the monodromies around punctures, so they were lambda and mu. And what we try to do, really, we try to do the following. So let me first redraw this picture. So this is, and you can think of it as a pair of pants with 2 marked points on the belt. Specified monodromies around the kind of all the legs, and you want to take this cycle, right? And you want to really try to cut this pair of pants along the cycle, and what you get is sort of direct integral, kind of schematically speaking, of this picture, where this is our new cut. This is lambda, this is mu, this is nu, and this is minus nu, and all of it you take kind of d nu. So this picture on the left is p nu, as we've seen, and this is m lambda mu nu, right? So here we take tensor product. So once again, if you just take this surface, so this is our old friend, disk with 2 marked points in the puncture, and you take its corresponding quantum cluster algebra and write its positive representation, that will be p nu, as long as you specify this monodromy. And if you take a sphere with 3 punctures and you take its corresponding quantum cluster algebra and you take its corresponding positive representation and you specify monodromies lambda mu and minus nu, this will be exactly this multiplicity space. All right, now I said that somehow you can see this quiver, you can see this in a cluster way. But remember, how did we even write these representations? We took the surfaces, we choose some quivers corresponding to this, describing their cluster structure, and therefore we should be able to see some some quivers telling us something interesting about the eigenvalues, right? And here's how we see that. So let me just copy this picture here. So we start with the picture here. That's what we see on the left in a cluster in which we are kind of ready to diagonalize the total Hamiltonians. And we instead we produce two pictures of the following kind. So well, it's going to be slightly tricky. 2, 3, 4. And I guess like that. So this is one picture, and another picture just kind of a rotated image of this same one. So here we have quiver Q prime. And if we label vertex over here, so this is vertex say 1, 2, 3, and 4, then our eigenvalues nu, so these guys here, the nu I is just the ratio of yi over n. In this case, n is equal to 4, right? All right, now the reason I'm showing these pictures is because I will in a minute or so I will talk about Gelfand-Teichmann systems, and we'll see actually these pictures. So I just like to point out once again that well, when you see this graph, when you see this subquiver, you should think of a quantum Toda system, because this quiver, this quiver defines a cluster structure on the Toda, on the phase space of the Toda system, and this subquiver, like over here, you see, and I guess there should be a double arrow in reality. Doesn't matter that much. This subquiver you see when you took your Toda system, you diagonalized its Hamiltonians, and you're trying to write a cluster quiver for the result of diagonalization, right? All right. So now let me just make one other remark about positive representations, and then I'll finally go to Gelfand-Teichmann systems. So remark will be as follows. So remember that our matrix, what our matrix was doing, it was just taking two punctures and swapping them. So this puncture will go here, this puncture will go here. But if we now think of how it acts on representation, what it does, it really just swaps the two representations. So what our matrix does is taking p lambda tensor p mu and mapping them to p mu tensor p lambda. And therefore, this family p lambda, so this family wants to be a braided monoidal category. And why I say wants to be rather than it is a braided monoidal category? Well, okay, it's obviously braided because we have a braiding given by the R matrix. It's kind of monoidal because we can tensor multiply, and the only factors in the composition are from this family. The problem is that if you want to say monoidal, you also want to say that there's a representation, a trivial object, right? So one that you multiply by and you get the, well, kind of like a unit in the algebra. So and obviously a trivial representation would be one-dimensional, and here everything is infinite dimensional. So there's, strictly speaking, there is no such thing as unit here. You can actually add it in a nice way. But then, in fact, it's even more. It's actually, there's actually even an action of SL2Z on this family. So it's actually even better than braided monoidal. But unfortunately, you know, all the objects are infinite dimensional. There are infinitely many of simple objects, and so on and so forth, right? So it's kind of this infinite dimensional analog of braided monoidal category. All right. Maybe once again, let me ask if there are any questions, and if not, I'll just discuss the Gelfand-Teichmann systems.
I'm sorry. So you are saying that the R matrix is well defined for?
Yes, our matrix is well defined. Yeah.
For any lambda and mu, right?
Yeah, for any lambda and mu. And the reason is that, remember, our matrix is just a product of 4 quantum Dell logarithms. And each of the quantum Dells, it acts on these representations. So for any lambda and mu, our matrix is well defined, yes.
So it doesn't have any poles in lambda and mu.
No, it doesn't. The matrix is just always well defined. And somehow this is exactly so the upside of this whole story is that everything is well defined. I mean, our matrices, cluster mutations, and so on. The problem is that everything is infinite dimensional. Now, in fact, you can, if you take very specific lambda and mu, you can, and moreover, not just very specific, but before we required that, before we required that lambda and mu, they're positive real numbers. Now, if we take very specific lambda and mu, which are not even real numbers, there's some specific complex numbers, you can actually see finite dimensional representations inside there, and then you'll have all the problems. So if you can go from this infinite dimensional family to finite dimensional representations, but then cluster mutations will start having poles and zeros, and our matrices will start having poles and so on, right? But still, you can take indeed if you can reduce this family if you want to. You can reduce the finite dimensional representation theory, and that's an very interesting direction of like that. Actually, no one is doing so far. So just an adverse of this thing. Yeah.
Okay. Thanks.
Yeah, absolutely. All right. So yeah, thank you for the question. Let me now say just a couple of words about Gelfand-Zeitlin systems. Right. So I realized that Anton Alexeyev and Jeremy Lane was like gave at least 4 talks by now about those, but let me still needless remind that well, what it's about, at least when we talk about quantum groups, it's still the same story as usual, that you consider UQGL1 sitting inside UQGL2 and so on, and sitting inside UQGLN. And well, you can take a center Z1 of UQGL1, and you can take a center Z2 in UQGL2, and so on, a center Zn in UQGLN, and all these centers they obviously don't sit inside one another. Sorry about that, but yeah, these are centers, and let's say that well, each center, so Zj. What is it, right? It's an algebra once again over rational functions of Q generated by the Casimirs of the corresponding UQGLK, right? So I'll write it as C I J, where I runs from 1 to J. All right. So for example, this guy over here, it's an algebra generated by our old friends C1, Cn. Right. Well, technically, I should write n over here now. All right, good. Now, and the way this UQ sit inside another, you can still think of just, you know, kind of loosely speaking, just matrices sitting one inside another. And therefore, what you get is so you get maximal commutative subalgebra. Inside UQGLN. So people usually denoted Gelfand-Zeitlin's subalgebra, and if they spell Zeitlin with Z, then it's GZ. But I was recently explained that Zeitlin should be spelled this way, so I'll just write GT. This is for Gelfand-Zeitlin. And what the subalgebra is, so this GTN is just, again, by definition, it's an algebra of rational functions of Q generated by all of these Cij, where I runs from 1 to J and J runs from 1 to N. Right, and now we can again ask a question. So can we see UQGLN minus 1 inside UQGLN in a cluster way, or well, from clusters? And the answer is, well, actually, yes, we can. And let me actually just copy this picture from the slide that I was, when I was preparing this talk, I kind of drew these pictures. Oh, sorry. Right. So I'll just copy this picture. And not only that I drew it, I also made a mistake there. So I kind of copy it and then correct it. All right, sorry about that. So it's example of SL4. Right. So this is our old friend. This is our quiver for UQSL4, for cluster structure in UQSL4, just coming from the surface where we have a puncture in the middle, 2 marked points, and we just glued 2 triangles together, right? So this is one triangle, and this is the other one. And now if we do many mutations, really a lot of those, then we can actually get to the quiver of this shape. And this, so I just chose SL4 as a minimal example where you can see all the intricacies of this quiver, but let me try to walk you through that. So you can see over here that this is a GL2 TODA, right? The quiver for the phase space of the GL2 TODA. You can see over here that this is the quiver for the GL3 TODA, right? You can see over here that this is GL4 TODA that was diagonalized. And that's why I spent so much time explaining this diagonalization process and positive representations. Now, let me maybe just, maybe let me make a copy of this quiver and label things. So here you see, this is GL2 TODA, and you don't see GL1 TODA because it's just, well, I mean, it's too simple. So I mean, well, kind of frozen variables. Some of the frozen variables really speak for it, but yeah, it's just too small of an example. So this is GL3 TODA. This is diagonalized GL4 TODA. And when I say TODA, I really mean quantum open TODA system, right? Now, how do you see quantum groups living inside one another, right? So if you wanted, for example, to put a UQSL3 inside UQSL4, right? How would you do that? So let me just do it once again. I'll copy this quiver. So what you will have to do, you will have to actually just take this GL3 TODA and diagonalize it. And what will happen as you do that, you'll, let me try to actually make this work. So you'll just have the quiver like that. And so now this is diagonalized GL3 TODA. Or maybe let me mark it. So this will be diagonalized GL3 TODA. And then you can indeed just embed one quantum cluster algebra into another by just saying, well, all these variables go to all these variables, and the symmetric functions of those go into TODA Hamiltonians. So I cannot really, I can't really say that really this algebra goes inside this algebra. Really, when I take W invariance, in this case, W is equal to S3, I can embed this guy inside here, but remember that UQSL3 still lies inside W invariance, right? And this is how you see the Gelfand-Seytlin subalgebra of UQGLN, really, and how you see all these embeddings. Now, nice things about that is, well, so over here, for example, I've chosen to embed all of them kind of as up as upper left corners, I could have chosen otherwise. I could, for example, let me copy that. Actually, yeah. So if I want to, for example, exchange this picture for this picture, so this could be done by cluster mutations. So this means that I'm just showing a quiver that kind of expresses. So this quiver expresses this embedding for me. But if I wanted to express another embedding, I would just draw a different quiver, which is kind of similar. But anyway, I can go into details if there are any questions about that. I can say it later. Yeah, maybe let me just say a few corollaries. So an upshot. So informally, yes. So first part, informally speaking, we see that this Gelfand-Zeitlin system, is kind of is a, well, if you wish, concatenation of quantum todas systems, and in particular, if you want to solve the eigenvalue problem for the Gelfand-Zeitlin system, it's already done for you, right? Because you just diagonalize the corresponding Hamiltonians of the quantum toda, right? So e.g., the eigenvalue problem for the Gelfand-Zeitlin system is solved already. Well, second part is the following. So there's actually another family of representations that appeared in the works of Gerasimov, Kharchev, Lebedev, and Dablezin, the so-called GKLO representations. So let me explain how they appear from this picture. So if we consider this positive representation P lambda, then we pass to the cluster, let me call it to the Gelfand-Zeitlin cluster chart. So the cluster chart given by this quivers that we've just seen a second ago, and then diagonalize every single Toda chain. Diagonalize all Toda systems. So if we do that, then what we get each time we diagonalize a Toda system, we get a unitary equivalence between two different representations. Oh, I see. There's a question. I'm sorry about that. Is there anything nice about the result of the result? Yeah, Dima, I'll answer this question in just 1 minute. Right. So what you get is the form when you diagonalize all the Todas. What you get is a unitary equivalence between positive representation and let me call it W. So this is Gelfand-Zeitlin representation or GKLO representation of UQSLN. And the reason it's GKLO is because names of the authors. And in particular, that means that the positive representations actually decompose without multiplicity with respect to this Gelfand-Zeitlin subalgebra, inside UQGLN. And obviously, and in reverse, you now know that the Gelfand-Zeitlin representations are, kind of form an analog of a braided monoidal category, but that's kind of a lame statement just because you know that these guys form and these are just unitary equivalent, right? Right, and that's that's it. So that's all I wanted to say. I'm in time for once. So yeah, I'll be happy to answer questions.
Maybe one more question. So Gerasimov, Kharshov, Lebedev, and Amblazin have some explicit formulas for the action of Chevalier generators
Yes.
of the quantum groups, and are they seen from this cluster construction?
Well, I mean, these formulas are precisely what you see when you so how to say when you write how Chevalier generators act in this cluster, and you can write it explicitly, and then you see what happens with those as you diagonalize all the todas. You recover all of them. Huh?
Yeah, so from this explicit expression of the Chevalier generators, you can. So you're saying you can see the different separators.
Yeah, exactly. So you just on the nose recover the GKLO formulas. So if you just write how generators of the quantum group act in this representation, this positive representation, diagonally, then you apply all this. Well, in this case, what 2 Whittaker transforms for GL1 toda, for GL2 toda, and for GL3 toda, you on the nose recover the Gelfand-Seytlin formulas. Well, maybe up to some normalization, maybe. You can, so when you do that, when you diagonalize, you do get just a bunch of quivers, but they're kind of a little degenerate, because you basically what you'll be seeing just frozen variables with a bunch of well, so you somehow, when you do that, when you diagonalize everything, your quiver falls apart into these blocks where you just have one frozen and a bunch of kind of variables like that. Maybe the other direction, I guess. And indeed, you can write, so you still can write formulas for Chevalier generators, but they will be complicated in this diagonalized world. Right. And to answer Dima's question, in this cluster, well, Chevalier generators are not particularly nice on one hand, but on the other, well, the Casimirs are very nice. So the Casimirs of the, well, again, the whole point of this cluster, right, is that the Casimirs of UQGLN are very nice in this cluster, right? So well, this is, so obviously the top Casimirs are just it's some symmetric function of the ratios of this variable to this one, this to this one, this to this one, and the lower Casimirs for GLK inside GLN is just the Hamiltonians of the toda. And another nice feature is that somehow this is there's this other work that I've been doing with Gus on providing cluster structure for this Braverman, Finkelberg, Nakajima, Coulomb branches, and kind of this is precisely the quiver where you see that quantum group is an example of such a Coulomb branch. And just again, so I will not explain that, of course, now, but kind of the story of this of this Coulomb branch is that you have some gauge theory, you have a gauge quiver that defines you the theory, and then basically what the work that we were doing is that taking this gauge quiver and producing a cluster quiver from the gauge quiver that will describe the cluster structure. And the gauge quiver here is nice indeed. So the gauge quiver here for SL4 would be just like that. Where you have C square, C cube, and the C to the 4. This is the so-called framing node, and you kind of see that this well, this more or less, these two pictures together more or less give you a recipe on how to, if you say gauge quiver of the gauge theory and you want to put cluster structure in the Coulomb branch, how you do that, right? That's more or less self-explanatory of how you pass from the right hand side here to the left hand side here, right? So in this way, this quiver, I think this quiver is nice. Right. I hope that answered the question.
Any other questions? Thank you very much.
Thank you.
So interesting. So okay, so we resume in 10 minutes. 5:15.